All right. So this class, we're gonna try to wrap up everything for this introduction class. Okay, so this is the final chapter. It's a solid waste management. So again, if we do a recap, right? So last class, we mainly talk about the pollution transport because as we said, pollution emission is a major thing. We want to control, reduce emission. But the transport is also quite important because if the, let's say the stacks are all building near the seaside and all the pollutions are just getting transported over the ocean, then we don't need to worry too much about it, right? It's not polluting our people, right? So it's not like we're just living downwind of a major stack there. So that will involve the wind patterns. So as we said, the wind is mainly just transporting these pollutants away. So the wind is caused by the pressure difference, right? It's blowing from the higher pressure region to the lower pressure region. And also this pressure is created by temperature difference. So generally the higher temperature will have a lower pressure, right? So that's why the wind will tend to be blown from the higher latitude, let's say the polar region to the equator region. So that's what gives us the regional and global patterns of the wind, right? The regional wind are something like land ocean breeze or land lake breeze, and also the mountain valley breeze, things like that. So in terms of the global wind, we have different circulation patterns, right? So we have different cells of the atmosphere having different directions of the wind, right? And also it creates this wind blowing from east to the west or west to the east. That's caused by the Coriolis force, right? So the Coriolis force is what happens on a sphere, right? The sphere is rotating, and some certain objects, when they're moving from south to north or north to south, the trajectory will get bent. So we said that on the northern hemisphere, this trajectory will bend towards the right, okay, caused by the Coriolis force. So an easier way to memorize this is we're living on the northern hemisphere, so we're always right, okay? We're gonna bend to the right. So that's why if you see these two cyclones or the hurricanes, you should be able to tell which hemisphere this is, right? So for example, for the picture on the left, we know that the hurricane is caused by a low pressure center, right? You have high pressure surrounding it. So theoretically, the wind is going to blow directly towards the center. And then it seems that the wind is bent towards to the right, okay? So that's what gives it the counterclockwise rotation, okay? Because it's bending to the right, so this is northern hemisphere. Okay, so similarly, for the southern hemisphere, you have these clockwise rotation here because the wind is basically bent towards left. Okay, you have this clockwise rotation. All right, so if we know the patterns of the wind, and then we know how the pollutants are being transported. Right, and then we talk about the atmospheric dispersion or the stability. Okay, so this is going to be a more regional. So it's going to be, I would say, a sub-regional type of transport, right? So we mentioned that if, let's say, this is our ground, and then we have the sun giving us the heat, right? If the ground is very cold, right? If it has a very cold temperature, it has a low pressure, right? It's going to have a high pressure, okay? So it's gonna tend to or prefer to just stay in the ground, stay on the ground, okay? Not to lift up. So under this situation, if our surface is very cold, then these pollutants tend to just float just near the surface. Okay, so it's very difficult for these pollutants to disperse away. And then for people who are living in these regions, they're just going to have to tolerate a high concentration of these pollutants. But if we have a relatively high temperature, let's say temperature is higher, then this air is going to tend to rise up, right? So that's called the unstable condition. which is better for the ventilation of the air pollutants. So because of this dispersion, people have different methods for designing the stack. Right? If I ask you, will a higher stack help for protecting our environment or for reducing the health impact of air pollutants? It will, right? Because a higher stack, if they are high enough that they can penetrate through this stable layer, then basically these pollutants are not going to be trapped here at all. Right? They're just going to get dispersed into the larger area. Right? So here is again this picture showing this global wind pattern. Right? You see at the polar region, because of the colder temperature, the wind is going to, in general, blow in this way. Right? But because our Earth is so large, it's going to break into different cells. Right? We have 3 cells on each hemisphere. And further, because of the Coriolis force, let's say the wind here bends towards right, wind here bends towards right, and here towards right. And then on the southern hemisphere, wind bends towards left, left, and left. Okay. So this is what gives us the global wind pattern here. So if I ask you again, where should we build those power plants, right? In the United States, then we should build it here, because it's better for the ventilation of the air pollutants, right? Because there are just so few people living on the ocean. So about the atmospheric stability, this is an example of why we would have a stable air that's just at the surface, right? This is because of the cooler temperature on the ground. So it's going to trap these air pollutants. Right? The same for here. You see the stack or the smoke coming out of the stack. They're just trapped within this, I would say, a shallow layer of atmosphere. Right? If people are living closely or nearby, then it's going to be bad for their health. Right? So that's what involved this stack design. So last class, we just talked a little bit about the principles. I think maybe this class we can get some numerical understandings of it, right? So here, what's showing is a stack sitting here, and then it's also emitting a lot of pollutants. We know that the air is going to have certain velocity coming out, right? So what happens with this smoke is that they're going to rise for a little bit because they have this momentum going up, right? And then when they reach to a certain height, then the movements that's going along the wind is going to be their major movement, right? So they're going to move towards or move along the wind, right? And then at the same time, they're going to disperse. They're not just going to concentrate in a single line here, right? They're going to disperse. So if we just draw the center line of this plume here, right, this dashed line here, this is a center line. So we know that the concentration is going to be the highest, right? Because it's nowhere to disperse. It's right at the center, right? But if we go to the edge of the plume, then the concentration will get lower. You can just imagine, let's say for this, this line here that's going across the center line. If we just look at infinitely far away places, the concentration will just equal to 0. But the concentration at the center is going to be the highest. So that's why people came up with this Gaussian model, because we know that the Gaussian basically describes this type of feature. Right? The concentration is the highest at the center line and the lowest when it's away from the center. Right? So then what people assume is that if you just look at this direction, which is in the y direction, okay? So the concentration, if I just draw y and then concentration. So the concentration is going to be the highest when y is equal to 0, and then it's going to be the lowest when y goes to positive infinity or negative infinity. So this is along the y direction. So the same will apply for the z direction, right? Because what should I do? Hide. Okay, here. So the same will apply for the z direction, right? If you just draw, this is z, this is concentration, and then the concentration will be lowest when it's infinitely far away, right? And then we may hit to a point where it's the ground. And let's say this is the ground. Okay, so but still we can approximate it with a Gaussian distribution. So that's why people came up with this equation here. Okay, so the Gaussian, if you just think about its form, normally people would represent it as, let's say, y squared divided by sigma squared. Okay, so this is a typical Gaussian equation. So because of that, people just multiply two Gaussians because we have the Gaussian in the y direction and the Gaussian in the z direction. So we have two Gaussian terms. That's showing here and showing here. Okay, so this is how people think about solving this problem. So there are a few parameters. So basically, this equation is used for solving the concentration of air pollutant at any x and y location on the ground. Okay, so if you see the parameters, you have x, you have y, and you have 0. 0 means z equal to 0. Okay, the height is equal to 0. We're just looking at the ground location because people care about what is the concentration at the ground because we are living on the ground, right? And then this h here, this is the effective stack height. This is the height of the plume. Okay, this term here. Right, so these are the parameters that's used in here, but it's it's used for solving the concentration basically at any location on the ground, right? And then on the right-hand side, it's dependent on the emission rate of the pollutant. Let's say how many kilograms of particulate matter emitted per second, right? It depends on the wind speed, the U term, right? And then depends on which y location you're looking at. Okay, so if it's 1 kilometer away from the center line or 10 kilometers away the center line, right? And then, so the h here is the effective stack height. So you see that the only remaining parameters are the sy, and sz. So sy and sz means the plume standard deviations, means how spread this plume is, because it depends on the wind condition. Right? If the wind is very strong, then it's going to just disperse a little bit, right? But if the wind is very slow, then it has more time to spread around. Okay, it depends on the wind condition. Right? So with this equation, we can basically plug in a lot of values and then just look at what is the concentration of certain air pollutants. So here, what I have is the example problem, our textbook. So maybe we can just quickly go over this. You don't have to do any calculation here, but it's better that you follow this process after the class. Okay. So this problem is saying that it has been estimated that the emission of sulfur dioxide from a coal-fired power plant is around 1.6 kilogram per second. Okay. So it's talking about 3 kilometers downwind of this stack. And then it's also under overcast summer afternoon. Because why does it tell the weather condition? It's because it's going to determine how spread this plume is. Right? Overcast means the sky is covered by clouds, right? During summer, normally the wind speed is slower, right? And then in the afternoon means that it's in daytime, right? It's better for the ventilation of the air. So it's asking what is the centerline concentration of the sulfur dioxide, basically at this location 3 kilometers downwind of the stack. So the stack height is 120, and then the wind velocity is 4.5 meters. Okay. So it also gives us the stack parameters, which has this height, diameter, exit velocity, right? The pollutants are coming out with certain vertical velocity, right? You have temperature of the plume, the pressure of the atmosphere, and then the ambient pressure of the atmosphere. right? So since we have this equation here, we can try to refer to the parameters, right? The E here is the emission rate, right? We have this term already in here. The E is ready, right? We have the U, which is the wind velocity. Then H is the effective stack height. Okay, so effective stack height is not directly the actual stack height because we need to consider the upward motion of the smoke, right? It's not directly spreading at this point. It's spreading further higher up, right? So the effective stack height is calculated by this. You have these actual stack height plus and delta H, which is accounting for this floating motion here, right? So the delta H is further calculated in this equation here. So a lot of them is just plugging in the numbers. So the Vs is the smoke or the exit velocity, right? You have this Vs, right? So the D is the diameter of the stack. U is again this velocity of the smoke. P is the atmospheric pressure. So when you plug in the numbers, P should use the unit of kilopascal. Okay. And then TS is the temperature of the stack, right? And then TA is the ambient temperature. So we also have the temperature. This is TS. And here you have TA, and then you have P. But one thing you have to pay attention is that when we talk about temperature, we should be using Kelvin. Okay, so we should plug in K here. So you see that the delta H can be solved, then H can be solved, right? The only unknowns in this equation. So y is equal to 0, right? It's talking about along the center line, right? So the only unknowns are the Sy and Sz, okay, which is the spread of this smoke here. So you see that the spread actually is getting wider and wider, getting larger and larger as you go downwind. Right? The spread at the beginning part, maybe just a few meters. But if you're talking about, let's say, 5 kilometers downwind, it's going to be larger, right? So Sy and Sz are going to increase with X. So the way we can find out Sy and Sz is to use this figure here, where the y-axis shows the Sy, and then the x-axis shows the X, which is downwind location. So we were talking about 3 kilometers downwind, right? We can just draw this line up. And then you have these 5 different categories, A, D, C, D, E, F. So they represent what is the stability of the air, right? Under very stable conditions, the plume, let's say, if we're having a stable condition, right? So the plume won't be able to spread too much. They're just going to get concentrated in here. Just like the plume in here, right? It's quite concentrated. But if it's under unstable condition, then what we know is that it's just going to get widely spread, right? This is unstable. This is stable. So if we look at this graph here, then the unstable condition will be A condition. And this is going to be the stable condition, right? You have smaller Sy and Sc. So basically, then the category that we're looking for, it should be dependent on the weather condition. It says that it's an overcast summer afternoon, right? So basically, you can find out the category of the stability based on this table here. So it's dependent on the local time, whether it's in daytime or nighttime, because we said that nighttime, the surface is cooler. It's easier to get stable conditions. It also depends on the surface wind. But for the overcast condition, if you look at the footnote, it says that the neutral class D should be assumed for overcast condition during day or night, which means that for our condition, we should use D. Okay? So if you go to the graph here, we just look at the D curve. right? You also draw out the 3 kilometer. So the SY and SZ should have the parameter that's corresponding to these 2 points, right? So it's a little bit difficult to directly read the number because it's in log scale. So that's why people also came up with this method to calculate what is SY and what is SZ, okay? So since we already find the stability condition, which is D here, right? And then it gives you this table showing some parameters like A, C, D, and F. So what people can do is you can use this equation, just plugging in this A value, right, 68. And then X is the distance downwind, that's 3 kilometers. And then to the power of 894. And then you can calculate what is SY. And so the same for the SZ. You have the C, D, and F parameters, right? And then further pay attention that for X smaller than 1 kilometer and X larger than 1 kilometer, you have different sets of CDF. So we should look at the C, D, and F values in this region because we were talking about 3 kilometers, right? So then we should plug in these 3 values, where C is 44.5, D is 0.516, and then F is minus 13, right? So if we have SY and SZ, then the only unknowns here are solved, right? So then we can plug in all the parameters and then try to solve what is the concentration, all right? Is that too quick or that's okay? Yeah, I think you also have a few practice problems in your homework, but you can also go through this from your textbook as well, all right? So then the rest of it is just plug in all the parameters. These are the equations we're going to use. We plug in these values and then find out that for this stack, if you're looking at 3 kilometers downwind of this pollution source here, the concentration of the sulfur dioxide is 1.45 multiplied by 10 to the negative 3 gram per meter cube. Okay. So how does it compare to the EPA standard? The EPA standard says that the criteria to tell whether it's polluted or not is 0.5 ppm in terms of 3-hour average, right? So we can further convert this mass concentration into mole fraction. So this is the contents that we learned earlier in the class about the unit conversion, right? So if you use this equation, then you can find out that actually this concentration is 0.55 ppm. It's a little bit higher than the standard, but we should still call it polluted air. Okay. So this is about the stack design. I hope that you can understand the process of calculating or evaluating the air pollutant concentrations, or in terms of designing the stack, right? If you're telling that 3 kilometers downwind, we need to maintain that the sulfur dioxide concentration to be below certain value, what should be the stack height? So you can do some calculations to design that, right? So that's the last bit about the air pollution, right? So the final part is the solid waste engineering. And so we talk about pollution in water, basically in liquid, we talk about pollution in the air, and then finally is the pollution in the solid, all right? So regarding the solid waste engineering, a lot of the time we're talking about the municipal solid wastes, okay? Or just simply garbage, right? So, so these municipal waste, solid wastes can come from residential sectors, commercial, institutional, construction, municipal service, or treatment plants, okay? So if you just look at the detailed fractions regarding what is the composition in each type, so you see that a large fraction are just paper products, okay? we can easily recycle them. Of course, food scraps, you probably have to dispose them, right? And then yard trimmings, this is biomass, right? We can probably harvest the energy out of it, right? Plastics, we can recycle some of them, right? Metals, we should recycle them. Rubber or leather, this is recyclable. Wood, biomass, right? And then glass. You see that actually quite a lot of them are recyclable, okay? But there are, right now, we'll talk later, but right now the total fraction of the recycled garbage in the United States is around 30%. So most of them are still dumped and go to landfill. So there are still quite a lot of work to do on recycling. So in the beginning of the class, I recommended this documentary to you, it's Plastic Wars, right? So right now, for a lot of plastics, they're labeled with the triangle, with the arrows, right? So you may think that they are recyclable, but a lot of them are not, especially for those very thin plastics. For example, the wrap or the box when you buy grapes, right? Some of them will put the grapes into the plastic box. So although it says that it's recyclable, it's not. So no countries are taking that right now. And so the labeling of the plastics, if you just look at this documentary, the labeling of the plastics actually generated more production of the plastics because we customers think that we can recycle them, but the fact is that we cannot. Right? We thought that we're doing a great favor to our environment, but actually we just consume more plastics. So this is it's labeled as a commercial strategy, but the environmental damage is pretty big. Okay, so if you're interested, you can look at this documentary. So in terms of generation rate, so for each person on average, we generate around 2.01 kilograms per day. This is 2010 data, which is quite reasonable if you just think about how much food you process, right? How much garbage you generate each day, right? So a large fraction of this solid waste is residential. And then for the low-income families, they have a lower production rate because they simply consume less, right? So the recycling fraction is 34.1% in 2010. I just look at the data for 2018. I think it's around 32%. We're down a little bit, but almost 1/3 of the garbage are recycled. So for the ones that are not recyclable, a major part of them is the putrescible waste. Okay, so those are the ones that can get degraded if you just put there for a long time. For example, the food from kitchens, stores, markets, and so on, right? Food processing facilities. What's making these materials worse is that if we just keep them in the landfill or keep them in the garbage, there can be bad odors getting generated, but also there can be liquid coming out. Okay, so the liquid is going to contain a large or very high BOD, right? Some of them get toxic metals inside, right? So it's concentrated with a lot of pollutants. So people also call this as leachate. Okay, so basically this is concentrated water that's coming out of these garbage, right? So here I'm just showing a picture of the, let's say a pond of polluted water coming out of the trash, okay? So this is a flow chart of how people treat these solid waste. So although it looks quite complex, but a lot of them directly make sense. So let's say it's a solid waste generation. Let's just think of a person, let's say myself, staying at home. I take off some wraps for my food, right? And then I just dump it in my trash can, okay, on site, right? And if, let's say I have a fancy trash can that just keep the glass bottles, Okay, so I can directly recycle them. I can utilize them, just wash it and use it, right? But for those that are not directly usable, it will get collected and then sent to some facilities, right, to let them process, and then maybe we can still use that. But for those that cannot be used, they will go to disposal. Okay, so this is a very simple diagram here. Because we're generating a lot of solid waste, so people will try to recycle, try to reuse the energy out of these waste here. So the background is that the Earth's mineral deposits or metal are limited, right? If we just don't recycle them, it means that we're going to consume more, right? And at the same time, we generate more waste, okay? So this is quite easy to understand. So that's why we need to consider about the resource conservation and recovery here. I think a new term in the terminology in the environmental engineering is what people call the green chemistry. Okay, so I think it has a quite fancy name and also fancy explanation to prevent the pollution before they happen. But actually, the central idea is that why don't we just replace the materials that we use so that we can conserve the other materials, right? To select the appropriate material that can enhance the material energy conservation or to minimize the environmental impact. So for example, let's say for the soda cans, right? So we consume a lot of metal from the soda cans. I think it's a recent news that some countries in Europe, they're trying to make Coca-Cola cans out of paper now. It's probably not metal, but the plastic bottle. Okay, so instead of using plastic, we try to use the paper products to make the bottle. So in that case, we don't need to generate a lot of plastic wastes, right? We can still conserve the environment. So the recycling, it's a quite easy idea to understand. So generally, there are three types of recycling. You have the primary recycling, which means that you just use the materials to make the same products. I think in some grocery stores, if you buy the milk in there, they're contained in a glass bottle. So when you buy them, you need to pay extra as a deposit, right? So when you send them back, they're going to clean it and then just put it on the shelf again after they fill the milk there. So this is just recycle with the same product, right? So there's secondary recycling, which is to use it to make different products. For example, the metal cans, right? We can melt them and then make the metal cans or some other metal components. There's also the tertiary recycling to recover the chemicals or energy out of the garbage. For example, the microprocessors, right? There are a lot of noble metals like gold, silver. That's why a lot of developing countries, they prefer to import these electronic waste and then get the noble metals out of it, right? Although it's a very small amount. So for the waste that are putrescible, right? So you can degrade them, right? People can use the composting facilities to extract the energy out of the organics. So basically, you can break down these organics, right, and also kill the pathogens. So what happens is that you can introduce the air, right, oxygen plus nitrogen, right? The bacteria can utilize these air, and then they can propagate, and then degrade these organics to reduce the BOD that's coming out of it. Right, so here is an example. You can use a blower to blow in the air, and then at the same time, you need to contain these garbage in a container, right? You can't just do it in the bare, let's say, in the air directly. Otherwise, you're going to generate a lot of odors. Right? So if I ask you, what is the process being used in composting? Right, since you use oxygen, that's going to be the aerobic process. Right? So the anaerobic doesn't involve any oxygen in there. Okay, so the other way to harvest the energy out of the waste is the combustion. So it's similar to the coal-fired power plant where we burn the coal particles, right? So we can convert these carbon into carbon dioxide, hydrogen into water, and if it contains sulfur, it will be transformed into sulfur dioxide. So combustion is a complex function of oxygen, time, and temperature. So as we introduced earlier in the NOx control, we don't want to use a very high temperature because the higher the temperature, the higher the NOx, right? But for the combustion of the waste, the thing is we cannot really burn it at low temperature because if it's low temperature, we cannot use all of the combustible materials. It's a quite complex scenario because the waste is not homogeneous, right? It's not uniform like coal particles, right? You can have a lot of plastics, let's say wood or paper. So each of them will have different combustion properties, okay? So furthermore, you generate a lot of toxic air. So that's why in these garbage incinerators, right? So when we put in these trash inside, when we combust them, there has to be an air pollution control equipment which remove the particulate matter, the sulfur dioxide or the NOx, and so on. Okay, so you can get these metal acids, ash, and particles, collect them, and then send them to disposal. Okay, so I would say that the major tool for us to process these solid waste is the landfill. Okay. So around 55% of all the municipal solid waste is going to landfill eventually. So if you imagine, or if you think back, we said that for all the solid waste, we recycle of around 33%. Let's make it higher, 35%, okay? And then 55% go to the landfill, right? So that will make it 90%, right? Around 10% of it. So maybe a fraction of them, we just burn it, right? We can harvest the energy out of it. But there's another fraction, they're just dumping the atmosphere. So it's not going to the landfill, it's not being recycled, it's just scattered in our environment, right? So here, I'll just use a very short video to show how the landfill works. So let me let this open. Sure. They'll also wait how much of the area is buried. This is the actual landfill. Normally it's on the fire. And then we're going to the area. So there's a compacted clay layer. This is mainly to prevent the leachate as we said, the liquid that's concentrated with toxins to prevent them from penetrating down to the soil. Have this pipe like every day we're going to place a cover, that's called the data cover. Then we're going to cover the final cover is a layer of soil that basically covers the entire area of the plant. Active gas cell. There are a lot of bacteria that generate composite gas. Called that function positive. I would say that landfill in modern cities, at least in the United States, they don't look very dirty, right? So people will basically, by using this type of design here, we're isolating the trash day by day, right? So you don't easily get, let's say, if a wind blow by, you don't have the scatter of the trash, right? And also, we can come up with a lot of extra decoration. Right? So normally they're built on hills, and when you drive by, you can see, oh, that's a grass. It's a grass hill, right? It looks very green there. You don't know it's a landfill until you really look at the satellite image, or if you look from high above. So as I said, for the design of the landfill, you have this cell structure, right? Each day, people will fit in one cell. And then after each day, you're going to cover it with a layer of soil, right? This is to prevent the wind from scattering these solid waste away. So finally, at the top, we're going to have this final cover, which is a thicker layer of soil that's going to further cap these trash down below. So in terms of the control, we have the leachate control. As you see, at the bottom, we have to have a very compact layer, soil layer, to prevent these leachate from going down. Because if it can penetrate our earth, penetrate our soil, it might as well go to the drinking water or the underground water, right? We know that the leachate is concentrated with toxins. We cannot let that happen, right? And then there's also landfill gas control. So in terms of the site considerations, you need to consider the public opposition, like public ideas. People don't like the landfill to just be built nearby our house, right? So you need to consider the flood hazard. If you have a lot of rainfall, then you might form a lot of leachate, right? Liquid. Transportation, soil condition, groundwater level, right? I guess one reason why we build these landfill on hills is that it's away from the groundwater, right? Because even if it penetrates down there, it's still going to take a pretty long distance to penetrate. So this is a quick quiz about what is the considerations for building the landfill. So I don't think we have time for that, but it should be all above, right? You need to consider what is the environmental impact, the collection, and also the size of the population. Another schematic diagram showing this cell by cell structure, right? This is a daily cell. You have daily cover, and then like the daily earth cover, right? We're not just dumping everything into a hole in there. Right? So another side view of it. So in terms of the leachate controls, leachate can be formed from rainfall, the groundwater and then the liquid from decomposition. So we have a lot of methods to prevent them from penetrating our soil, right? And then for the collection, we used under-drain pipes to remove the leachate. The leachate composition, as we said, contained ammonia, organic pollutants, halogenated hydrocarbons, heavy metals, and salts. It's very polluted, very concentrated. And after we collect them, we still need to treat them, right? We cannot directly dump them somewhere else. So we can use the biological or the physical chemical methods to purify them before we discharge them into the environment. So this is another side view of the leachate pipe, right? Then this is basically a cell of the landfill. Another picture, right? See, we can store quite a lot of trash in each landfill there. So these are the pipes for collecting or pumping the leachate for processing, right? And these pipes are for collecting the landfill gas, right? We can still harvest the energy out of it. We can generate heat coming out of it. These are the pipes for transferring the leachate. And finally, there are methane gas being produced because they're explosive. We can harvest the energy. Again, for the design, we need to consider the population, the fuel density, trash generation rate, which is related to how much trash can be generated. So finally, when we close the landfill, when it's completely full, we can't just go away without treating the rest of it, right? We need to put on a final cover. So the final cover is to prevent the moisture from entering the landfill, because in that case, we're forming the leachate again. And then the final cover consists of surface layer, biotic barrier, and so on. Okay, so it's a quite complex design to prevent the formation of these liquid pollutants. So finally, maybe we can use 1 minute to review this course. Okay, so this is the introduction of environmental engineering. As you can see, for each section, it's really just glancing through the topics. So for the last section of this course, we talk about the air pollutants, right? The criteria air pollutants, there are 6 of them. We talk about the PM, sulfur dioxide, nitrogen dioxide, talk about these unit conversion, meteorology, and stack design. So for the solid waste management, we discussed the design of the landfill and the leachate control. But if you think back on the beginning of the class, we spent quite a lot of time on the chemical principles. I know that maybe many of you that don't like these chemical ideas. I would say that in the future, you are going to use that. You're probably going to use it, but definitely for the environmental engineering students, you're going to use these ideas for the next few years. We talk about mass and energy balances, right? In terms of water quality, we discussed the DO, the dissolved oxygen, right? The DO sag curve. For water treatment, there are a lot of terminologies: coagulation, flocculation, sedimentation, filtration, disinfection. Right? The wastewater treatment, we have the primary and biological treatment. Okay, so this is the overall contents of this course. So at the end, I can do a shameless self-advertising. So again, I'm a relatively new professor in the department, and my focus area is mainly on air pollution. It's quite different from the other environmental engineering professors. So we have a lab called the Particle Measurement and Technology Laboratory. Right now we have three graduate students and 5 to 6 undergraduate students. So we're working on quite a lot of projects on air pollution. So why is air pollution important? Last year, I'm just listing the last year's event, okay? We have wildfires, right? In Australia, in Western US, it's very severe. It's dumping thousands of tons of these air pollutants into the atmosphere. It's leading to environmental issues, human health issues. Also last year, we have this severe outbreak of the disease associated with vaping. So by the way, if any of you are using these products, please don't, okay? Our studies show that even one puff, you're going to inhale the metal that's going to be much over than the daily limit that's recommended by the FDA. Okay, a lot of metal particles inside. A lot of countries or cities in the US are troubled by these urban pollution because we have so many cars. It's generating a lot of air pollutants. And I guess more importantly these days is the transmission of the SARS-CoV-2 virus. So there's, I think it's on maybe 2 days ago or 3 days ago, the CDC finally admitted that the transmission of these COVID-19 virus is mainly done by airborne transmission, which is done by aerosols. So we are working on aerosols, and we have a few projects looking at these different research topics. So, so finally, I mean, feel free to contact me if you're interested in the project. And finally, I want to thank you all for spending your efforts on this class, and hopefully there are some useful contents that you can use in the future. All right. So that's all for this class, and let me know if you have any questions. So our final exam is on Wednesday.